In this lesson, we're going to introduce benzene and the concepts of aromaticity and anti-aromaticity. Aromaticity is a powerfully stabilizing form of resonance. In order to be considered aromatic, a molecule must meet certain criteria. Specifically, an aromatic compound must have a cyclic structure, a p orbital on each atom in the ring, usually referring to sp2 hybridization. All atoms in the ring must be coplanar, in the same plane. And the ring must follow Huckel's rule, which means it must have 4n plus 2 pi electrons, or an odd number of pi pairs. The expression 4n plus 2 is just a way of generating specific numbers of pi electrons. In the expression, n can be any non-negative integer, like 0, 1, 2, etc. Plugging 0 into the expression gives us 2 pi electrons. Plugging 1 into the expression gives us 6 pi electrons. 2 electrons is 1 pair, an odd number of pairs. 6 electrons is 3 pairs, again an odd number of pairs. Let's take a look at a few examples to see how all this works. First, we have benzene, the quintessential example of an aromatic molecule. We can clearly see that benzene has a cyclic structure, and that all 6 carbon atoms in the ring are sp2 hybridized, and therefore have an unhybridized p orbital. The 6 carbon atoms in the benzene ring are in fact coplanar. Whether the atoms in the ring are coplanar isn't always going to be immediately obvious. In general, if all the other criteria for aromaticity are met, and there's nothing preventing the molecule from being planar, then we can assume that it's planar. Now, with respect to Huckel's rule, we can see that benzene has 3 pi bonds inside the ring. And of course, a pi bond is simply a shared pair of pi electrons within a pi bonding molecular orbital. So each pi bond contributes 2 pi electrons, meaning benzene has 6 pi electrons. And we can get the value 6 by plugging 1 into the 4n plus 2 Huckel expression. And of course, 6 pi electrons is 3 pairs of electrons, and 3 is an odd number of pairs. So benzene follows Huckel's rule, and because benzene follows the other criteria, it's aromatic. Let's take a look at a more challenging example. Here we have the Cyclopentadienyl Anion. Let's start by looking at this first resonance structure. We can see that the molecule has a cyclic structure. 4 of the carbons are involved in pi bonds, making them sp2 hybridized, and that means that they have an unhybridized p orbital. But what about that carbon on the bottom, the negatively charged carbon? In this drawing, it certainly looks sp3 hybridized. But if we apply our knowledge of resonance, we can see that that lone pair is actually delocalized. If you focus on the 3 carbons on the left, you can see this is really just an allylic anion. If we draw a second resonance structure for the cyclopentadienyl anion, we now see that in this second drawing, the lower carbon is in fact sp2 hybridized. Remember that any structure with resonance is in reality a blend of all of its resonance structures. Because that bottom carbon is sp2 hybridized in this second resonance structure, it really is sp2 hybridized in the molecule. That means that all 5 carbons in the ring are in fact sp2 hybridized, and therefore all 5 have an unhybridized p orbital. We'll assume that the 5 carbons in the cyclopentadienyl anion are in fact coplanar, and that just leaves Huckel's rule to look at. So how many pi electrons are in the ring of the cyclopentadienyl anion? Well, in the first resonance structure, we clearly see 2 pi bonds, so that's 4 pi electrons. But we've also established that the lone pair is also delocalized. If we look at these 2 resonance structures, we can see that the lone pair in the first resonance structure is actually a pi bonding pair in the second resonance structure. That means that the lone pair is in fact involved in a pi bond. And that means that the cyclopentadienyl anion actually has 6 pi electrons. And as we already saw with benzene, 6 can be achieved by plugging in 1 to Huckel's rule. So we can see that the cyclopentadienyl anion is in fact aromatic. In the next example, we introduce a heteroatom into the ring. Here we see furan, which looks a good bit like the cyclopentadienyl anion. Furan is clearly cyclic, and if we follow the same logic that we apply to the cyclopentadienyl anion, we will see that all 5 atoms in the ring are in fact sp2 hybridized. One of the 2 lone pairs on the oxygen can participate in resonance, forming a pi bond to the adjacent carbon. That means that the oxygen is in fact sp2 hybridized, and that gives all 5 atoms in the ring an unhybridized p orbital. We'll again assume that the 5 atoms in the ring are coplanar. Now, what about Huckel's rule? Once again, we have 2 pi bonds, so clearly we have at least 4 pi electrons. But the oxygen atom now has 2 lone pairs. If we look at some of the other resonance structures for furan, we see that in any given structure, only one of those lone pairs can participate in a pi bond. If you think about it, the other lone pair is stuck in an sp2 orbital. This means that one of those 2 lone pairs can be counted towards Huckel's rule. So the 2 pi bonds plus one of those lone pairs gives us 6 pi electrons. And we can get 6 from Huckel's rule by plugging in 1. 4n plus 2 would be 6. As a general rule, you should only count 1 electron pair towards Huckel's rule on any given atom. You need to assert that those electrons can in fact participate in a pi bond. We see that the lone pairs on the oxygen of furan can in fact participate in resonance. They can form a pi bond to one of the adjacent carbons. But only one of those electron pairs on the oxygen can participate in a pi bond in any given structure. The other will always be stuck as a lone pair in an sp2 orbital. Our last example should give us a nice review. Here we have pyridine, one of my least favorite compounds. Pyridine is a relatively common organic solvent, and because it's an amine, it's also used as a weak base. The issues I have with pyridine are, first, it smells absolutely awful. And second, it supposedly causes testicular atrophy, hence my rather inaffectionate nickname for it, Stinky Shrinky. If we look at the structure of pyridine, we see it closely resembles the structure of benzene. It's clearly cyclic, and we can easily see that each atom in the ring is in fact sp2 hybridized. Again, we'll initially assume that the ring is planar. Now, with respect to Huckel's rule, we can clearly see the 3 pi bonds, giving us 6 pi electrons. But what about that lone pair on nitrogen? Well, remember our rule of thumb. We can only count 1 pair of electrons towards Huckel's rule on any given atom. And that nitrogen is already involved in a pi bond. It already has a very clear set of pi electrons associated with it. And that means that we cannot count that lone pair towards Huckel's rule. That lone pair is stuck in an sp2 orbital and is not delocalized. Only the 6 electrons in those 3 pi bonds are counted. And again, we can get 6 electrons by plugging 1 into Huckel's rule, so it's aromatic. Pyridine has an odd number of pi pairs, 3 pairs in the ring. Well, every positive in the universe is balanced by a negative. And with the existence of aromaticity, we also have anti-aromaticity. Anti-aromaticity is a powerfully destabilizing arrangement of pi electrons. In a sense, anti-aromaticity actually disrupts resonance, which is why we don't consider it a form of resonance. Just like we saw with aromaticity, to be considered anti-aromatic, a molecule must possess a certain set of criteria. In fact, the first 3 criteria for anti-aromaticity are the same as those for aromaticity. To be considered anti-aromatic, a compound must have a cyclic structure, it must have a p orbital on each atom in the ring, usually meaning sp2 hybridization. All of the atoms in the ring must be coplanar in the same plane, and that means that the only difference between aromaticity and anti-aromaticity is the number of pi electrons in the ring. To be considered anti-aromatic, the ring must contain 4n pi electrons, or an even number of pi pairs. So let's take a look at a few examples. First, we have cyclobutadiene. Cyclobutadiene is clearly cyclic, and we can see that all 4 atoms in the ring are sp2 hybridized. We'll again assume that the 4 atoms in the ring are coplanar. When looking at the pi electrons, we can see those 2 pi bonds, and that means 4 pi electrons. And we can get 4 pi electrons when n is 1 in the expression 4n. And of course, it's also an even number of pi pairs. And that means that cyclobutadiene is in fact anti-aromatic. Our next example is the Cyclopropenal Anion. The molecule is clearly cyclic, and if we look at the first resonance structure, we can see that the lower 2 atoms in the ring are in fact sp2 hybridized. As drawn, that top carbon looks sp3 hybridized. But just as we saw with the Cyclopentadienyl Anion, that lone pair is in fact delocalized. It's going to participate in resonance. And we can see that by drawing out just one more of the resonance structures for the molecule. So now we've established that all 3 atoms in the ring are in fact sp2 hybridized. When counting pi electrons, we have 1 pair clearly from that pi bond in the original resonance structure, But in drawing the second resonance structure, we see that the lone pair becomes a pi bond, and that makes that lone pair a pi pair. So the cyclopropenal anion has 4 pi electrons, which is 2 pairs, an even number of pairs, and that means it's anti-aromatic. So let's take a look at one last compound, cyclooctatetraene. Cyclooctatetraene is clearly cyclic, and we can see that all 8 atoms in the ring are in fact sp2 hybridized. Now, the cyclooctatetraene structure has an 8-membered ring, and when rings get really large, the coplanarity of the atoms in the ring is not necessarily assured. We'll come back and revisit the planarity of the ring once we've addressed the pi electron count, which in this case is really straightforward. There are 4 pi bonds, so we have 4 pairs of pi electrons, or 8 pi electrons. And we can get 8 pi electrons by plugging 2 into the 4n expression above. So we might initially believe that the cyclooctatetraene molecule is in fact anti-aromatic, but it's not. And that's because the molecule doesn't have to be planar. The 8-membered ring is big enough to pucker out of planarity into a tub-like shape. So think of the two possibilities here. Cyclooctatetraene could in fact be planar, but by being planar, cyclooctatetraene would actually meet all of the criteria for being anti-aromatic. And anti-aromaticity is a powerfully destabilizing arrangement of pi electrons. That large ring can pucker out of planarity, and when it puckers out of planarity, it ceases to be anti-aromatic because it no longer has that criterion. The 8 atoms in the ring are no longer coplanar. In that form, it's simply non-aromatic. It's neither aromatic nor anti-aromatic, like water. The 8-membered ring in cyclooctatetraene is large enough to bend out of planarity, and in doing so, it actually becomes more stable because it becomes non-aromatic. And in the universe, everything gravitates towards stability. In comparison, the 4 atoms in the ring of cyclopentadiene are stuck being coplanar. The ring is simply too small to allow enough free rotation to bend the molecule out of planarity. Essentially, cyclopentadiene doesn't have a choice. It has to be coplanar, and therefore it is in fact anti-aromatic because it meets all the other criteria. The larger ring in cyclooctatetraene is capable of bending out of planarity and avoiding anti-aromaticity, which makes it more stable than it would be if it were in fact anti-aromatic. So why is aromaticity so powerfully stabilizing? And why is anti-aromaticity, which is almost the same as aromaticity, the only difference being the number of pi electrons in the ring, why is anti-aromaticity so destabilizing? We can explain this using molecular orbital theory and a device called a frost circle. A frost circle allows us to predict the relative energies of the pi molecular orbitals in a cyclic system. It's actually pretty straightforward. We start by drawing the molecule with one vertex at the bottom of the structure. We then enclose the drawing with a circle centered at the center of the molecule. The relative energies of the pi molecular orbitals are then inferred to be at the intersections of the circle and the vertices of the molecule. Once we know the relative energies of the orbitals, we populate those orbitals with electrons following Hund's rule, the Aufbau principle, and the Pauli exclusion principle. So let's see how this works with two examples. First, we have benzene, which we know is aromatic. We draw the benzene with one of its vertices at the bottom. We draw a circle positioned at the center of the molecule with a radius equal to the distance from the center to one of the vertices. Each intersection of the circle with a vertex of the molecule gives us the relative energy of a molecular orbital. So in this case, we have 6 pi molecular orbitals, represented here with little horizontal lines. Orbitals below the midpoint of the circle are considered bonding molecular orbitals. Those above the middle of the circle are anti-bonding molecular orbitals. Orbitals aligned with the center of the circle, which we don't see in benzene, would be considered non-bonding molecular orbitals. So in this case, we have 3 bonding molecular orbitals and 3 anti-bonding molecular orbitals. Now we're ready to start populating those orbitals with electrons. And of course, benzene has 6 pi electrons. We start by placing 2 in that lowest energy orbital, then 1 electron in each of those 2 degenerate orbitals at slightly higher energy, and then place the last 2 electrons, again 1 in each of those 2 degenerate orbitals. Once we're finished, we can see that all 6 pi electrons are placed into pi bonding molecular orbitals. And remember that all 6 of those electrons initially were in p orbitals, non-bonding orbitals. So all 6 of those electrons have been lowered in energy, And that's how we explain the extra stability associated with aromaticity. In the second example, we have cyclobutadiene, which we know is anti-aromatic. Again, we start by drawing the molecule with one of the vertices at the bottom. We draw a circle positioned at the center of the molecule with a radius equal to the distance from the center to one of the vertices. We see that the circle intersects 4 vertices, and those intersections imply the relative energies of 4 molecular orbitals. In this case, we have 1 bonding molecular orbital, 1 anti-bonding molecular orbital, and 2 non-bonding molecular orbitals. Now, cyclobutadiene has 4 pi electrons. We populate the orbitals starting with the lowest energy orbital available, placing 2 into that bonding molecular orbital. The last 2 electrons would be placed into the 2 non-bonding orbitals available. And remember Hund's rule. We don't pair up electrons in degenerate orbitals until we're forced to. So what we see is 1 electron in each of those 2 degenerate non-bonding orbitals. This means that only 2 of the electrons, which started in non-bonding p orbitals, have moved down in energy into that bonding molecular orbital. The other 2 electrons are still in non-bonding orbitals. And of course, they're not even paired. If we look at how the orbitals are actually occupied, cyclobutadiene should only have 1 pi bond, because only 1 pi molecular bonding orbital has been occupied with 2 electrons. We should expect cyclobutadiene to have only 1 pi bond and 2 unpaired electrons. As far as I know, cyclobutadiene does not exist. And if it did exist, it would actually behave as a diradical, having 2 unpaired electrons. The disruption of that second pi bond explains why anti-aromatic molecules are so unstable.